Hi, in this video, we're going to talk about bit operations and we'll start with the shift operation. So hopefully, as you can see by now, bits are very precise and can be very compact way of representing informations. And given that, bit operations can be actually very efficient. And bit operations are supported since the very early days of computing. So by bit operations, we mainly talk about two categories of operation. One is shifting, the other one is doing and or not, and other kind of logical operations. And we're going to talk about shift operation here. So there are two types of shift operation. One is left shift, and it is denoted by two less than signs, and it takes two operands. First, it's the number to be shifted, and then the second is the shift amount in number of bits. So in this example, the number that we're left shifting is in binary 1 0, and we are shifting left by just 1 bit. So that 1 0 becomes 1 0 0. Okay, and another example this is 1 1 in binary, and we are left shifted by 2 bits, which then becomes 1 1 1 1, but followed by 0 0. So you can see that because there were no digit to the right of 1 1 in the original number, so when we shift the number over, then we kind of create like 2 bits of kind of gaps, right? And those gaps are filled with bit 0 and 0. It's also very interesting to look at what it really means in decimal. So 1 0 in decimal is the number 2, and we left shift by 1. It becomes 1 0 0, which in decimal is 4. Okay, now what about 1 1? 1 1 in decimal is 3, and when we're left shifting 3 by 2-bit positions, that becomes 1 1 0 0, and if you convert it to decimal, it is the number 12. So 3 becomes a 12, and I wonder if you see a pattern in these two operations. And if you don't see them immediately, maybe you can try a few more examples and see if you can spot the pattern. Now, what it actually is, as it turns out, is that if you are left shifting a number by n, then you are effectively multiplying that number by 2 to the power of n. So if you look back at an example here, let's say 3, we're left shifting by 2, so 2 to the second power, that's 4, right? So the result is basically 3 multiplied by 4, which is 12. Now we actually see the same thing in decimal as well. So if let's say a number, let's say 30, and if we are in decimal, okay, if we're left shifting 30 by 1-digit position, then that 30 becomes 300, right? And we're basically, that's 10 times what the original number is. So this is pretty much the same idea, or yeah, just kind of like this. Now the next shift operation we're going to talk about is the right shift operator, and it is denoted by 2 greater sign. So it's pretty much analogous to the left shift operation. So it takes 2 operands. The first operand is the number to right shift, and then the second operand is the number of kind of digits to right shift by. And just as examples, so here is the binary 1 0, and if we right shift by one digit, it becomes, the 1 comes to this position, so it becomes just 1, right? And the second example is in binary 1 1 1 0, and if we right shift by two positions, then these 1 0 here is kind of fall off the edge, and then we are left with 1 1 in these two positions. Now, the reason I feel this with 0 0 is in the original number, you can kind of imagine there are probably like an infinite number of zeros, or there can be an infinite number of zeros to the left of this number, right? So when we right shift the whole thing by two digits, then we're leaving kind of two void in this position, but since there are infinite number of zeros to its left, so we can pull in two zeros here and put it there just to make things clear. And well, again, it will be interesting to kind of look at what these numbers are in terms of decimals. So 1 0 is 2 in decimal, and the result is 1, which in binary and decimal it means 1. Right? And 1 1 1 0, it is in decimal 14. Okay, and the result of 1 1, that's in decimal 3. So 14 left shift by 2 binary digits is resulting 3. So again, try to look at this and see if you can spot any pattern, or if you don't, immediately try to work out, try to do right shifting a few more numbers and see if you can spot the pattern. So what it is that a binary number right shift by n is equivalent to that number floor divided by 2 raised to the n power. So let's check that. And basically in the first one, it's a number 2 left shift, right shift by 1. So 2 raised to the first power is 2, so it's basically 2 floor division by 2, and that gives us 1, right? And in the second example, where right shift by 2, so 2 raised to 2 square is 4, and so we are effectively doing 14 floor division by 4, which is 3. And again, this is the same idea that we have in the decimal numbers, that if a decimal number is right shift by n number of digits is equivalent to that number, well, this should be floor division by 10 raised to the nth power. So for example, if we given the number 30, and if we right shift by one digit, that is pretty much the same as 30 divided by 10 raised to the first power, which is just 3. So now you get a chance to practice your bit shifting skills. So there are just a few problems here. I'll try to work it out by hand and then verify with my answers. And here's a hint. I mean, some of these numbers, they're not specified in binaries, and it would help a lot if you actually convert them to binary first before you bit shift them. And here are the answers. So I just want to say for the last one, it's actually kind of, you can hopefully see the answer immediately because it's left shifted by 4, and each hex digit is just 4 bits. So basically, this is just shifting a one hex digit, and that's why this is the result.